We're in Rosen section 1.4, Discrete Mathematics and its Applications, and the topic is propositional functions or predicate logic. And we're talking about quantifiers, which will be used to bind variables in propositional functions. We've encountered a couple of, one propositional phrase, one proposition already, all men are mortal, that contains a quantifier in it. That's the word all. And here's another one. Some cats do not have fur. And that's another quantifier that we will need some symbology for, as we'll see here. And we'll use two mainly quantifiers. One is the universal quantifier. You can think about that meaning for every or for all. And its symbol is an upside down A. And then the existential quantifier means there exist or some values exist for which this is true, and it has a symbol of a backwards capital E. And then the way we situate these in terms of the symbols is we put them in front of the propositional function that we're trying to bind, and we describe the variable. So here we have for all x, p of x, and there exists x, p of x. For all x, p of x says that p of x is true for every x in the domain, so that means we also have to specify the domain for the proposition, or for the variable. And this line says there exists x, p of x, says that p of x is true for some x in the domain. Again, we have to describe the domain for x. And these quantifiers bind the variable that they modify so that when they are placed in front of a propositional function, it actually turns it into a proposition that will have a truth value. Let's take a look at the universal quantifier. Here again we have for every x, p of x, or for all x, p of x. And if we use x is greater than 0 as p of x, we designate the domain of x to be the integers, then for every x, p of x is false, because there are many integers that we saw earlier that make this statement false. So it's not true for every integer. But if we change the domain to be the positive integers, then for every x, p of x is true, because every positive integer is greater than 0. And if we change the propositional function to x is even, we go back to the integers as our domain, then for every x, p of x is false, because some integers are not even. So you can see that the truth value depends upon the domain and on the propositional function. All right, so this symbol is read for some x, p of x, or there exists x, p of x, or for at least one x, p of x. And we'll use x is greater than 0 as p of x. Our domain will be the integers. And then there exists x, p of x is true, because we did find one, and there are several for which p of x is true. That is also true if we change the domain to the positive integers. If we change p of x to x is less than 0, but we retain the positive integers as our domain, then there exists x, p of x is false. And with the integers, there exists x, p of x is true when x is even is p of x. There's another quantifier that we will encounter on occasion called the uniqueness quantifier. And it's the existential quantifier with an exclamation point after it. And it says that p of x is true for one and only one x value in the domain. A couple of different ways to say it. There is a unique x such that p of x, or there is one and only one x such that p of x. So for this first example, if p of x is x plus 1 equals 0, use the integers, then there exists one and only one x p of x is true, and that value would be x equals -1. It's the basis of algebra. But if p of x denotes x is greater than 0, then there exists one and only one x p of x is false, because several integers are greater than 0. Interestingly, we can actually uh, use a more complicated phrase and avoid the use of the uniqueness quantifier, although it is handily compact. But here's an equivalent phrase. Here we see that we have there exists x p of x, and for every y, if p of y is true, then y is equal to the x in question. So there can be only one value for which is true if this is true. All right, what are some ways we can think about these quantifiers? A very common way is to think about it in terms of a loop. If we encounter a quantifier, we just loop through all the values in the domain to see if the propositional function is true for those values. To evaluate a for every loop, then p of x needs to be true for all values. And if we determine that it's false for some value, then we can stop and say that for every x, p of x is false. To evaluate an existential quantifier, we will loop through all the values, and we can stop if we find one that is true, because we only need one to be true for there exists x, p of x to be true. But if we don't find any for which it's true, then there exists x, p of x is false. And you can even do this in a sense if the domains are infinite. Just have to keep in mind all possible values. Once again, the truth value depends not only on the propositional function, but also on the domain. So for u being the integers and p of x is less than 2, then there exists x p of x is true, but for every x p of x is false. If you use the negative integers and p of x is the statement, x is less than 0, then both there exists x p of x and for every x p of x are both true. And if I have a very constrained domain, the set containing 3, 4, and 5, then p of x will be x is greater than 2 in this case. Then both there exists x p of x and for every x p of x is true. But if I go back to my original p of x is less than 2, then both there exists x p of x and for every x p of x is false. So this illustrates how domain selection will affect the truth value of a quantifier-bound propositional function. One last slide on the precedence of quantifiers. They have the highest precedence of all the logical operators. So that in this example, for every x, p of x, or q of x, means that these two are tied together and the x and q of x remains unbound. In fact, this is not even a proposition. It is a propositional function in the variable x inside the q of x propositional function. For every x, p of x and q of x in parentheses means something different. In this case, it's a proposition because we are binding x and p of x and q of x to be the same thing, and we're saying it's that one of them is true for all values of x. It is a common mistake to intend this second expression when writing this first expression. So just be careful of context and try to insert parentheses where they need to be. And this is a discussion of quantifiers that are used to bind variables in propositional functions to create propositions, which will be true or false depending on the propositional function and the domain for the variables.